Welcome student into the lecture series of subject heat transfer. It's part number 6 of chapter number 2, conduction heat transfer. In this lecture, we will discuss about heat conduction through extended surfaces, means the fins examples. Also, we will discuss about estimation of error in temperature measurement in a thermometer well. So let's start the example number 1. It's a given data, a very long 25 mm diameter copper rod having a thermal conductivity of 380 watt per meter degree centigrade extends horizontally from a plane heated wall at 120 degree centigrade. The temperature of surrounding air is 25 degree centigrade and the convective heat transfer coefficient H is 9 watt per meter square degree centigrade. We want to find out the heat loss, and second one is how long the rod be in order to be considered infinite. So from the given data, first of all let's make a list. Here D is a 25 mm, convert into the meter, so 0.025 meter. Conductivity is given, the temperature of the plane heated wall T0, that is the end of. First of all, make a list of given data and then start the solution. Here the diameter is given in 25 mm, so please convert into the meter, so it's 0.025 meter. Then after the conductivity K, and here the heated wall temperature is 120 degree centigrade, which is also a fin base temperature, and that is T0 is equal to 120 degree centigrade. Atmospheric temperature denoted by TA, and that is 25 degree centigrade, and convective heat transfer coefficient denoted by H, that is 9.0 watt per meter square degree centigrade. Here the length of rod is not given and we want to determine the heat loss. So heat transfer, for the heat transfer, if the considering the case number 1, the fin is infinitely long, we have the equation of heat loss, that is Q fin is equal to KAM T0 minus TA, that is temperature difference. So from that equation, here the conductivity K is given, area that is pi by 4 T square, from the diameter we can calculate it. Now temperature also given, T0 that is 120, TA that is equal to 25, but M is required for the calculation of the heat loss from the fin. So first of all we calculate the M. So we know that the equation of M, that is equal to under root of H into P divided by K into cross sectional area. Here the P, that is the perimeter, and D is the diameter. So P is equal to pi into D, that is the perimeter, and A, that is the cross sectional area, we know that pi by 4 D square. If we mathematically simplify that equation, we get under root of 4 into H divided by K into D. Here one D cancel out, one pi cancel out, and the denominator 4 shifted to the numerator. So we get the value of M is equal to under root of 4H divided by K into D, that is equal to under root of 4 into 9 divided by 380 into 0.025 is equal to 1.945. Now by using the value of M, we can easily calculate our heat loss from this equation Ka into M into delta T, that is T0 minus Tm. Let's put the value in this equation. So first of all we write the equation, Q is equal to K multiply by area, that is pi by 4 D square, and multiply by M multiply by temperature difference. Now K is equal to 380 pi by 4 square of the diameter, and directly taken the value of M, which is already calculated, 1.946, T0 temperature and TA temperature. So by the calculation we get the value of Q fin, or heat loss from the fin, is equal to 34.48 watt. That is our first answer. Now we want to find out the length of rod to be considered infinite. That second part is very important. Since there is no heat loss from the tip of fin, and so that tip of an infinitely long rod, and such as it behaves as if the tip were insulated. So that an estimate of the validity of this approximation can be made by comparing the following two expressions for the fin. The one expression related to the q fin is equal to k into a into m t0 minus ta infinitely long fin, and q fin is equal to k into m multiplied by t0 minus ta into 10 hyperbolic ml, the fin with insulated tip. So equivalent results are obtained if 10 hyperbolic ml is greater than or equal to 0.997 or ml is equal to ml greater than or is equal to 2.646. So the rod can be considered if infinite, then L is greater than or is equal to 2.646 divided by m. Putting the value of m, it is already calculated, that is 1.946, so that the length of this rod when considered infinite is equal to 1.36 meter. Let's learn about the example number 2, and the data is it is required to heat oil to about 300 degrees centigrade for a frying purpose. A ladle is used in the frying. The section of the handle is 5 mm multiplied by 18 mm. The surroundings are at 30 degrees centigrade. The conductivity of the material is 205 watt per meter degree centigrade. If the temperature at a distance of 380 mm from the oil should not be reached 40 degrees centigrade, determine the convective heat transfer coefficient. So here in the given figure, the handle of the ladle is given. Suppose here the oil is there having a temperature of 300 degree centigrade. So we are considering the initial temperature or the base temperature of this ladle as a fin, that is T0 is equal to 300 degree centigrade. And from this end, when x is equal to 0, here from this end when x is equal to 0 to the 380 mm, the temperature of that point is 40 degrees centigrade. The surrounding temperature is 30 degrees centigrade. The atmospheric temperature is 30 degrees centigrade. It's a cross section 5 mm multiplied by 18 mm of this handle. So we want to find out the convective heat transfer coefficient H. Now when you solve any kind of example, first of all formulas is very important. So here in this topic, from where we can find out the convective heat transfer coefficient H. So we have equation M, and from equation of M we can easily calculate the value of H. So if you want to find out the value of H, you have to first calculate M. Now let's find out how can we calculate the value of M. So here is the given data T0, that is based temperature of the fin, that is 300 degrees centigrade. B is 18 mm, converting into meter 0.018 meter. Y is equal to 5 mm, 0.005 meter. Length is equal to 380 mm, 0.38 meter. Conductivity is 205 watt per meter degree centigrade, and atmospheric temperature is 30 degrees centigrade. Now we already learned about this equation. It is very important equation, and assuming the fin to be long one, and so that the temperature distribution of the fin is T minus Ta divided by T0 minus Ta is equal to e raised to minus mx. By using that equation, we are already derived one equation, Q is equal to H A M delta T. So here in this equation, if we are removing the minus sign, so the term will change from T minus Ta to T0 minus Ta divided by T minus Ta is equal to e raised to mx. Now putting the value of T0, Ta and T, so we get 300 minus 30 divided by 40 minus 30, and putting the value of x, that represent the particular distance, that is 380 mm, and so that e raised to m multiplied by 0.38. By the mathematically simplification, we get e raised to m into 0.38 is equal to 27. So m is equal to 8.673. Now we can easily find out the value of h. We know that m is equal to under root of h into p divided by k into a. So h into p divided by k into a, removing the under root, so that the square of the 8.673 and is equal to 75.22. So now p is equal to perimeter, and the perimeter is equal to b into h multiplied by 2 divided by area b into h. So here h into bracket 0.018 plus 0.005 into 2 divided by k is equal to 205, and area is equal to 0.018 multiplied by 0.005. So by the mathematical simplification, we get h is equal to 75.22 multiplied by 205 multiplied by 0.018 into 0.005 divided by 0.018 plus 0.005 multiplied by 2. So we get the value of h, that is 30.17 watt per meter square degree centigrade. Let's learn about the example number 3. Find out the amount of heat transfer through an iron fin of length 50 mm, width 100 mm and thickness 5 mm. Assume the thermal conductivity 210 kJ per meter over degree centigrade and convective heat transfer coefficient H is equal to 42 kJ per meter square over degree centigrade. For the material of the fin and the temperature at the base of the fin as 80 degree centigrade, also determine the temperature at the tip of the fin if the atmospheric temperature is 20 degree centigrade. So first of all, list out the given data. Here the length is given 50 mm is equal to 0.05 meter, b is equal to 100 mm is equal to 0.1 meter, y is equal to 5 mm is equal to 0.005 meter. Thermal conductivity K is equal to 210 kilojoule per meter over degree centigrade, H is equal to 42 kilojoule per meter square over degree centigrade, T0 is equal to 80 degree centigrade, and atmospheric temperature TA is equal to 20 degree centigrade. Generally, the unit of thermal conductivity K is given in watt per meter degree centigrade, and the unit of convective heat transfer coefficient is given in watt per meter square degree centigrade. Here the both unit given in kilojoule per meter over degree centigrade and kilojoule per meter square over degree centigrade. So let's start the example solution. Here we want to find out the amount of heat transfer through the iron fin. So we have to apply the equation of heat transfer. Q is equal to under root of P into H, K into A, T0 minus TA into 10 hyperbolic ml. So for that, P, that is the perimeter, A, that is the area, and M, that is equal to under root of HP by Ka. So for calculating the heat transfer, we require these three terms, P, A and M. So first we calculate the perimeter, that is equal to 2 into B plus Y. So putting the value of B and Y, B is equal to 0.1 and Y is equal to 0.005, we got the value of perimeter 0.21 meter. The cross sectional area is equal to B into Y, so 0.1 into 0.005, and we get the value is 0.0005 meter square. The m is equal to under root of hp by ka, so h is equal to 42 and k is equal to 210. Now you seen that here no need to convert the unit from kilojoule per meter square over degree centigrade into watt per meter square degree centigrade, because upper side in the numerator h is there and the denominator side k is there. So both hour cancel out. That means if we are convert hour into the 3600, so here both will cancel out, so no need to convert this unit conversion and directly taken the value h is equal to 42 and k is equal to 210. So we get the value of m by the mathematical simplification is equal to 9.165. So now we can solve this equation. Q is equal to under root of P into H K into A multiply by T0 minus TA into 10 hyperbolic ml. So P is equal to 0.21, H is equal to 42, A is equal to 210, K is equal to 210, A is equal to 0.0005. T0, that is the temperature, initial temperature, base temperature, that is equal to 80, atmospheric temperature is 20 and 10 hyperbolic m into L. So here m is equal to 9.165 and length is equal to 0.05. So now we find out the Q is equal to 24.75 kilojoule per hour. Now another we want to find the temperature at the tip of fin. So for that we are using the equation theta divided by theta 0 is equal to T minus TA divided by T0 minus TA is equal to cos hyperbolic m into L minus x divided by cos hyperbolic m into L. We want to find out the temperature at tip where x is equal to L. So in that equation, temperature distribution equation, we are putting the x is equal to L, so that x is equal to L, then we get the equation of temperature distribution, that is T minus TA divided by T0 minus TA is equal to 1 divided by cos hyperbolic m into L. So now temperature of atmosphere is 20 degree centigrade and base temperature is 80 degree centigrade. So T minus 20 divided by 80 minus 20 is equal to 1 upon cos hyperbolic ml, and so that T is equal to 60 divided by cos hyperbolic 9.165 multiplied by 0.05 plus 20. So the temperature is 74.21 degree centigrade at the tip. Let's move to the example number 4. A motor body is 360 mm in diameter, outside diameter is given, and 240 mm long. Its surface temperature should not exceed 55 degree centigrade when dissipating 340 watt. Longitudinal fins of 15 mm thickness and 40 mm height are proposed. The convection coefficient is 40 watt per meter square degree centigrade and determine the number of fins required. So we want to calculate the number of fins. So atmospheric temperature is given, that is 30 degree centigrade, and thermal conductivity also given, that is 40 watt per meter degree centigrade. So that is the figure. The figure is most important. The interpretation of the figure from the given data is most important part in this example. Here the motor body is given as per the example, having a outside diameter is 360 mm and the fins is given, and the fin, longitudinal fin having a thickness of 15 mm is given. So let's calculate this example. The total heat transfer is given 340 watt. The given problem is a case of heat dissipation from a fin losing a heat at the tip, short fin situation, so that the rate of heat transfer in such a case is given by Q is equal to under root of P into H into K into A multiplied by temperature difference T0 minus TA multiplied by 10 hyperbolic ml plus H by Km divided by 1 plus H by Km into 10 hyperbolic ml. So first of all we have to calculate the value of m. So m is equal to under root of Hp by Ka. For that we have to calculate perimeter. So we know that 2 into b plus y and area is equal to b into y. Supporting this value, H is equal to 40, B equal to 0.24, Y is equal to 0.015 and K is equal to 40. So by the mathematical simplification, we get the value of M 11.9. Again, by multiply by the length 0.04, we get the multiplication of ml is equal to 0.476. Now we use this multiplication m into L. So now supporting the value in the previous equation, as I shown, Q is equal to under root of Hp into Ka multiplied by temperature difference T0 minus Ta into bracket 10 hyperbolic ml plus H by Km upon 1 plus H by Km into 10 hyperbolic ml. So here inside the bracket P is equal to 2 into B plus H multiplied by value of conductivity, convectivity transfer coefficient, cross sectional area, temperature difference 55 minus 30, product of M into L, and that is the H, and divide by K into hyperbolic ml. So after the mathematical simplification of this whole equation, we get the value of fin heat transfer from the fin is equal to 21.77 watt. Now that heat transfer, or we can say that the heat loss from the single fin, we want to calculate the number of fin. So number of fins is equal to Q total divided by Q of single fin. So total heat loss given, that is 340, and that is the heat loss by single fin, that is 21.77. So we get easily the number of fin, that is 16 fins is required. Let's learn about the example number 5. A longitudinal copper fin, thermal conductivity is 380 watt per meter degree centigrade, 600 mm long and 5 mm diameter, is exposed to air stream at 20 degree centigrade. The convective transfer coefficient is 20 watt per meter square degree centigrade if the fin base temperature is 150 degree centigrade. Determine the heat transfer and the efficiency of the fin. So when calculate the two data, heat transfer and the efficiency of fin. So it's a given data, length is equal to 600 mm, convert into the meter, 0.6 meter, determine diameter of the fin, that is 5 mm, 0.005 meter. The fin base temperature is 150 degree centigrade. Air stream temperature, that is the atmospheric temperature, is 20 degree centigrade. Thermal conductivity, as I said, 380 watt per meter degree centigrade, and convective heat transfer coefficient H is equal to 20 watt per meter square degree centigrade. So we know that the equation of heat transfer, neglecting the heat loss from the end surface, the heat transfer from the fin is given by Q is equal to K into A into M multiplied by T0 minus Ta into 10 hyperbolic M into L. So calculate the value of M under root of Hp into K. Here the perimeter is equal to pi into D and the cross sectional area pi by 4 D square. Again by the simplification we get under root of 4 into H divided by K into D, so that H is equal to 20 and D is equal to 0.005. So value of M is equal to 6.49. So now Q is equal to K is equal to 380, cross sectional area is equal to pi by 4 D square, M is equal to 6.49, temperature difference 150 minus 20, and 10 hyperbolic M into L is equal to 6.49 multiplied by 0.6. So that the heat transfer is equal to 6.29 watt. Now from this value of Q, we can convert this value into the kilojoule per hour. So 6.29 multiplied by 3600, so 22644 joule per hour, or we can say that 22.644 kilojoule per hour. Next, we calculate the efficiency of fin, and for fin insulated at the tip, the efficiency of fin is given by the equation tan hyperbolic m into L divided by m into L. So here we already calculate the value of m, that is 6.49, and L is equal to 0.6. So tan hyperbolic 6.49 multiplied by 0.6 divided by 6.49 multiplied by 0.6. So we get the efficiency 0.2566, convert it into the percentage, so it is 25.66 percentage. Let's start our new topic, estimation of error in temperature measurement in a thermometer well. For estimating error in the value of temperature measured by the thermometer dip in a thermometer well, the theory of extended surfaces is very useful. A thermometer well is defined as a small tube welded radially into the pipeline through which a fluid whose temperature is to be measured is flowing. As we seen in the figure, here the thermometer well is shown in figure. Here is the cross section of the pipeline. It is the temperature T0 at x is equal to 0. Inside the thermometer well, here the oil is there. The thickness of this well is delta. The length of this well is L and the diameter is D. Inside this pipeline, the fluid is flowing and we want to find out this temperature of the fluid flow inside the pipeline by using that thermometer well. As I said, L is equal to length of well or tube, D is the diameter of pipe, inside diameter of the pipe, and delta is equal to thickness of well or tube, Tf, that is the temperature of fluid flowing throughout the pipeline, and T0 is the temperature of pipe wall. When the temperature of the fluid flowing through a pipeline is higher than the ambient temperature, the heat flow from the fluid towards the tube well along the well. Consequently, the temperature at the bottom of well becomes colder than the fluid flowing around. Obviously, the temperature shown by thermometer well will not be the true temperature of the fluid. This error may be calculated by assuming the well to be a spin protruding from the well of a pipe in which fluid is flowing. It may be assumed for simplicity that there is no flow of heat from the tip of the well, so that tip of the well is insulated. The temperature distribution at any distance x measured from pipe wall along the temperature well is given by theta x divided by theta 0 is equal to Tx minus Tf divided by T0 minus Tf is equal to cos hyperbolic m into L minus x divided by cos hyperbolic ml. Say equation number 1. At x is equal to L, we have T suffix L minus Tf divided by T0 minus Tf is equal to cos hyperbolic m into L minus L divided by ml. So is equal to 1 upon cos hyperbolic m into L, that is thermometric error. Say equation number 2. Here the T suffix L is the temperature recorded by the thermometer at the bottom of the well. Now perimeter of the well, P is equal to pi into D plus 2 delta, or here near equal to pi D, and cross sectional area is equal to pi into D into delta. So P divided by cross sectional area, that is 1 upon delta, and so that M is equal to under root of HP by K is equal to H divided by K into delta. Thus the temperature measured by the thermometer is not affected by the diameter of well. From the equation number 2, it is obvious that in order to reduce the temperature measure error, ml should be large, necessitating the following: the large value of H, heat transfer coefficient, small value of K, thermal conductivity, long and thin well, the pocket protruding, small tube may be placed obliquely or inclined if necessary to provide a longer intersection of thermometer. So it's the end of part number 6. We will meet in the part number 7 of this chapter, and we conclude our chapter with a last topic. So thanks for watching, keep learning, and wish you good luck to all.